Hello and welcome to another EGR/PHY 321 Engineering Dynamics lecture video, Stephen F. Austin State University. Today what we're going to be doing is we're going to continue on. We're going to do some examples from section 17.2. We're on the 15th right here of April, right? Some brief reminders is that we're looking at having our COLO 11 assessment on Monday. That's going to cover all of section 17.1, which is what we finished last week. So you have a little bit of a delay, so we have some time to kind of catch up a little bit. But COLO 11 is due on Monday, and the homework for section 17.1 is due on Friday. So make sure to get that taken care of, and we're going to continue on with the same process which we've been working out with beforehand. The next COLO 12, is going to be the following Monday, and that's going to cover section 17.2 and 17.3, which we plan to finish on Monday of next week. All right, so that being said, I kind of want to look a little bit about the slides from last week or last class, right? Focusing on 17.2. And so here I go, scroll down. Here we go. And so we talked about this idea, before in the previous section we talked about energy, and this time we're talking about impulse momentum, right? And so the main equation that we're going to start with, a lot of these problems are going to be building off of this theory right here. Okay, so this is going to be our theory equation. Is just the applying the momentum method that we had discussed in previous sections or previous chapters, right, when it had to do with particles. But this time we're considering for rigid bodies. And remember, for rigid bodies, kind of a general statement is we can do it for both linear but also angular momentum for all the points centered on these plane bodies, right? So we're doing bodies. We're doing plane bodies, right? So this is not planar motion here. So we're only looking at forces and velocities in the x and y direction. And we said that really the process, let's see here, the process that where the best to apply these types of problems is a solution of problems that are involving time and velocity. Okay, and so and also kind of any kind of impulsive motion and impacts. When we talked in 17.3 about eccentric impacts, this is going to be kind of one of the founding principles, right? So that's just the stage for what I wanted to complete today. Last class we worked through sample problem 17.8. This might have been a mistake in the last video. I might have called it 17.7. I do want to work out problem 17.7 today. The reason why I want to do that is because we're going to work a homework problem afterwards, and this kind of helps to kind of set the framework for how we can analyze the homework problem. And so that should hopefully help out with your homework for at least section 17.2. So here we have two gears. They're set up in such a way that we have a gear A, right? So you have a gear A and we have a gear B. They give us the mass for each of them, right? The gear A has a 10 kilogram mass and a radius of gyration of 200 millimeters, right? Notice how that's different than the 250 that you see here. What it's giving us is we're not able to model this specifically like a disk or any such thing. So it gives us radius of gyration so we can determine its mass moment of inertia. They also give us the mass and the radius of gyration of the smaller gear. We say that the system is at rest when all of a sudden a couple of m, right? So it's going in this counterclockwise direction. So think of this as applying like a torque, right? So if we applied a torque to the gear B, and we have the moment for that, for the couple, it's applied to gear B. And then if we're neglecting friction, this is friction in the joints of the gears, right? We are to determine the time required for the angular velocity of gear B to reach up to 600 RPM. And we are also to determine the tangential force that occurs between B and A. So that tells us a little bit about, this is an internal, right? The external force or moment that's applied is M, right? And so what we're going to have to do is since we're trying to find that force in between them, okay, we're going to have to use the impulse momentum method and assume each gear separately. And so we can do that, and that would be the best way to solve this type of problem. So let's look at our notes here and start writing down what we what we have, our sample problem. This is sample problem 17.7. All right, the knowns. So the first known that they give us is the mass of A, so MA is equal to 10 kilograms. And then the radius of gyration. So radius of gyration, remember that we typically denote that by the letter K, right? So we can call that K bar for A. That's equal to, and we'll put that in meters, 0.2 meters. And then we know the mass of B, that's equal to 3 kilograms. And then the radius of gyration for gear B is equal to 0.08 meters. It gives us the magnitude of the moment M, and that's equal to 6 Newton meters. And then we say the angular velocity, maybe say the angular velocity at state 2, right? So this is basically after a certain amount of time, the angular velocity of gear B, so maybe I'll have to say omega B, right? In fact, since it's starting at rest, we can just call it omega B. We'll just leave it as omega B, and that's 600 RPM. Which we know if we multiply that by its revolution, so we have 1 revolution on the bottom, that's equal to 2 pi radians. And if for a minute, we have a minute on the top, divided by 60 seconds on the bottom, this should give us radians per second. And if we calculate that out, that should be equal to 62.8 radians per second. So that's my angular velocity of B after some time. The unknowns. The unknowns we're looking for is the time, right? So the time required, so T. And then the tangential force that the gear B acts on A. Okay, so we'll just call that, I guess, force F. All right, so let's think about this problem a little bit. Let's look at the theory here. The theory, as I had mentioned beforehand, we're going to be using our momentum method, right? The system momenta for state 1 plus the system external impulse from state 1 to 2 is equal to the system momenta state 2. We're going to apply this to the two gears separately, and so we'll do the same thing we had done before, right? Our momentum diagrams very similar to what you're seeing here. We're going to apply that to each of the gears. We know that for the mass moment of inertia for each of the gears, that should be equivalent to the mass multiplied by k bar squared. Okay. And then ultimately, we'll just have to go through and apply our mass moment relationships as we kind of go forward here. So let's look at, if we need anything else, we can put stuff up there. So solution. So we should have everything we need for this problem. I don't think we're missing any information here. Yes, the radiuses. That's going to be important. So let's put the radiuses down here. RA is equal to 250 millimeters. Actually, let's put that in meters. 0.25 meters. And then RB is equal to 0.1 meter. So let's get our solution here. All right, so let's consider the, let's look at the motion, what's going on here. We have the big gear and the small gear, and they're coming into contact, right? And so we understand that there should be, after some time, we're going to have an angular velocity, and that would be omega 2. Similarly, since these are kind of keyed together, since they're gears and we're assuming no slipping, that means this big guy should be moving at omega, not omega 2. Let's call that omega b, right? Let's call that omega b, and this would be omega a. And this is general for any case here. And the way that we relate these two is that we recognize that the velocity at the point of contact, okay, so we'd say maybe this is the velocity of c, right? We can relate the two angular velocities by the fact that the velocity should be the same at the edges of these gears. And so we can say that the velocity c should be equal to, well, we can define that if we know the radius RA, and we know the radius RB, right? And both of those are given. And so my velocity c should be equal to RA omega a, and this should also be equal to RB omega b. So if I want to find omega a, I could just say that should be equal to RB over RA multiplied by omega b, which is equal to, and RB we had said was 100 millimeters, so 0.1 meters over 0.25 meters. Omega b, and if you calculate that out, that should be equal to 0.4 omega b. And since omega b is equal to 62.8 radians per second, that gives my omega a as being equal to 25.1 radians per second. So we understand the general motion here. This is what we're going to be ultimately going for, but let's first now break it down into our let's break this down into the momentum equation for each of the gears. So I'm going to take this thing here. All right. Oh. Copy, paste. So we're going to make our momentum diagram for the large gear. Okay. So we're saying this plus this equals this. So we first think about the system momenta of state 1. The system momenta of state 1, assuming that we have the center here, and we'll say that we'll call that location A. Right? There's nothing going on, right? There is no, here, our I bar A, omega A, and this would be like the initial omega A, maybe omega A naught, that should be equal to 0. Right? So there's nothing going on there, and then we have any of the forces that are acting on this multiplied by the time that it takes. And since we're talking about a discrete time interval of t, we'd say, all right, we look at the reaction forces at A. So you have AY multiplied by the time t. We have AX multiplied by the time t. Those are the two forces that are acting for the pin connection. And then we have the force that comes from the moment that's on the small motor. Remember, now the small motor is going in the counterclockwise direction. That means that we're going to see at the point of contact, which we call point C, there's going to be a force. And with the force we're laboring it is just the force multiplied by the time that it takes it. And then afterwards, since this is pinned in location, we only have one momentum term, and that's going to have to do with the rotation. And here we'll call this I bar A, and then we'll say omega A. Right? Where generally we're saying omega A, the initial condition, that's just equal to 0. So if we want, what we can do here is we can apply our momentum equation. And so what we have on this term here, this is a 0. Actually, I need to define what we're doing our momentum. Let's do our moments about A. And the reason why we choose this is because that will negate the reaction forces at A. We don't really care too much about that, and it makes it simple for our calculation for the inertia, or I'm sorry, the momentum terms for the rotating disk here. And so if we go through this, we're saying going counterclockwise is positive. Here we have nothing because there's no motion. Then the only moment that's being caused here is a negative, and then we have to consider the fact that it's the moment, which is the force multiplied by the distance here, and remember the distance is RA, so it'd be RA multiplied by the time. This should be equivalent to, and then we're looking at the rotation of the disk, and since we said counterclockwise is positive, this will be a negative term, and this will be I bar A omega A. So since the negatives here are going to cancel out and we have no 0 here, we can find that Ft should be equal to I bar A omega A divided by RA. And we'll leave it in this general form here. We didn't really talk too much about I bar A in this equation. We can find I bar A as well as I bar B. That's equal to the 1/2 the mass multiplied by, make sure I get this right, mass multiplied radius of gyration. So, right? Did I forget a 1/2 term up here? I think I did. No, that's not a. It's not a disk. Okay, I'm getting confused here. So this is not 1/2. It's just it's just the mass. This would be K bar A quantity squared. This would be equal to mass of A is 10 kilograms and Ka is 0.2. Quantity squared, that means that should become equal to 0.4 kilogram meters squared. And then for our mass of B, K bar B, quantity squared, that's equal to 3 kilograms, 0.08. So 3 kilograms, 0.08 meters squared. That will give 0.0192 kilogram meters squared. So we have our I bar A and I bar B. We know what RA is and we know what omega A is. So we can find that if we plug in the values for that, Ft just becomes equal to 40.2 Newton seconds. So we're going to hold off on doing anything with this until we look at now the smaller gear. So the smaller gear looks like this. And then I'm going to mess up here, copy that, say there, and do this one more time. Okay, so what we're having here is we're doing the same momentum diagram, except, and we're going to go the moments about B. All right, so I cut the video there for a second because I wanted to make these a little bit larger. In the initial case, we know that the I bar B omega b initially is equal to 0, right? Because it's not moving, it's at rest. Then we have the reaction forces at B, so we'll say By multiplied by the T there, and then I come over here and say, let's say Bx multiplied by T. That's our impulses for the what's it called? The impulses for the pin reaction, right? For the joint there. We also have our moment. Remember, our moment was acting in the counterclockwise direction. We'll call that mt. And then we have the force that's being applied at the location C, right? And that's going in the opposite direction. Remember, this is an internal force here, so they should have equal and opposite vectors. Sorry. My iPad's messing up a little bit. That's okay. And this would be an ft. And the great thing about this is if we do the summation of moments about B, we should find that, remember this is a radius, right, RB. Then we should get that this is equal to, so this plus this is equal to, and then the rotation now is going to be going in the counterclockwise direction, so that's going to be I bar B, and we'll say that's just omega B. Okay. So now we get the same thing, very similar to what we'd seen before. We have our system momenta for state 1, that's equal to 0, plus then the external impulses. So we have the moment that's being applied here. If we're doing this about B, that's a positive, so we say mt. And then we take away the external impulse for the force that's at the edge here. So that would be the FRBT. This should be equal to, and then I bar B omega B. So what we can rearrange things here. We know the moment, right? And if I divide through by RB, let's take this. We can say T is in, let's do this. Let's divide through by RB, right? So we'd have M over RB T minus FT is equal to I bar omega B over RB. And if we solve for T here, I can get, we have Ft is then equal to M over RB T, I'm sorry, I'm not doing Ft here. We have T is then equal to RB over M multiplied by Ft plus I bar omega B over RB, right? And so if we know that the Ft, which we had found before, from before, the case from before here is 40.2 Newton seconds, should be B, right? I missed that there. We know what I bar B is here. We know what omega B and RB are. We know RB in the moment. That means we can plug in all of our values and get that our time is equal to 0.871 seconds. So that's the answer for the first part. And then lastly, we know that Ft is equal to that 40.2 Newton seconds. So then the force and then just be equal to the 40.2 Newton seconds multiplied or divided by time. And once we get that, we get that the force is equal to 46.2 newtons. So that's you know, I skipped a few of the steps there, but that's okay. I really kind of wanted to that should be the simple stuff. The more difficult stuff would be setting up the momentum diagrams here. Okay. And so the reason why I chose this example problem to work through is because I wanted to work through a problem from the homework. and it's similar in terms of its setup, right? So this is from the textbook. It's problem 17.76, and this is an interesting problem because we have this gear arrangement, right? And gears A and C are attached at rod ABC, which is free to rotate around the B, right? So this B location here, that's kind of like a frictionless bearing, right? While the inner gear B is fixed, okay? So this is going to stay in place. This gear is staying in place, and this is allowed to rotate around, right? So while this rotates around, we would expect that the gears themselves are going to kind of rotate in the opposite direction, okay? Or I guess rotate along the same direction. But if you think about it, if this part is moving downward, right, that means that this is moving in this direction. That means we need to have that counter rotation. This might be something you would see in a clock or maybe some sort of mechanical system. So it's an interesting setup, right? But it comes back to we can apply the momentum relationships to the various portions of what we're trying, or of various parts of this assembly here. Knowing that the system is at rest initially, determine the magnitude of the couple M. So now the unknown here is the couple M, which must be applied to rod ABC. And then it gives us the information for our knowns, right? So it says at a time of 2.5 seconds later, the angular velocity of the rod is 240 RPM clockwise, right? So since the angular velocity of the rod is clockwise, that means that the moment should be clockwise as well. All right, so gears A, and it tells us the information about the mass, or I'm sorry, the weight of gears A and C. And then we can consider them as discs of radius 2 inches. Okay, and then the rod is ABC is weighs 4 pounds, right? We look at the radiuses here. We know those are given as 2 inches. And yeah, I think that's pretty good here. So let's go through this. And so once again, this type of problem, I'm not really going to concern myself too much with getting the numerical answers, right? Because your numbers are going to be a little bit different from all the ones given here. I'm going to just focus on the process and how we set this type of problem up. So let's go to the right here. So we're doing homework problem 17.7. The knowns, the things that we're given is that the time is going to be equal to 2.5 seconds. We have the omega of ABC is equal to 240 RPM. And if I convert that to radians per second, that would be 2 pi radian over 1 revolution. And then this would be 1 minute divided by 60 seconds. So 2 times 240 is 480. 480 divided by 60 should be 8. So we could just say that omega ABC in this case is 8 pi radians per second. And the reason why we're just leaving this general is because that's going to be the way it spins up to, right? The other things that it gives us here are the masses, or in a sense we can find the mass. We know the weight of A is equal to the weight of C is equal to 2.5 pounds. And the weight of ABC is equal to 4 pounds. And then we have the disc radius R, which is equal to, and we'll just put that in feet, so 2 by 12 foot. All right. So the unknowns, I guess the unknown, the single unknown, is we're trying to find the moment M, right? And this is going to be going in a clockwise direction. The theory here, simply stated, is our system momenta. I think that's, I'm going to leave this because we have one other drawing that we have to consider here. That we have the 8 inches, right? The total length of the rod is 8 inches. So we say the length here is equal to 8 by 12 feet. But other than that, I think we're okay for right now. I can probably put this to the side here. In our theory, remember, system momenta for state 1 plus the system external impulse from 1 to 2 is equal to the system momenta for state 2. And for a disk, right, we're modeling this as a disk itself. We know that that should be 1/12 for, no, I'm sorry. So we'd say I bar for a disk. So we'd say I bar for A is equal to the I bar for C, which is just equal to 1/2 M R squared. And then the I bar for ABC, right? We can model that as being a rod. So it's 1/12, and that would be M L squared. Yes. All right. So let's first talk a little bit about the motion here. So our solution, when we're working our solution out, we need to find some information about omega A and omega C, right? The rod here, and then each of the discs are on the edges here. And we know that this is rotating about with omega ABC. That means that there exists a velocity VC, right? And if we were to calculate the VC, right, this VC would be the same, right? It would be equal to the same as VA, right? Because they're the same distance across, right? So this distance across here is L by 2. And so this would be like my VA. So that should just be equal to the total length of BC between the center and the edge there. So I guess what we could do is say L by 2 multiplied by omega ABC, right? And so if we can also consider that if we look at, say, for instance, we're looking at this part here, this should also be rotating omega C, right? And so since we can kind of consider that this is almost looking at a specific point, if we picked any kind of point in position, we know that we can relate the omega c to the velocity c, right? By saying that the omega c should just be equal to my velocity c over r. And the same thing for omega a, would just be equal to the velocity a over r, but they should be the same, right? So omega a is equal to omega c, which would be equal to those values there. Now we can pull this all back to omega abc because we know that the L by 2, right, this just equals 2r. Because we know that there's that third block in the middle, right? We know that there's this distance here. These are r's here. So the half distance of the rod is just equal to 2r. So ultimately, we can say that to make this really simple, we know that VC, this just becomes 2r omega ABC, right? And since the velocities are the same here, we can just say that this is equal to 2r omega ABC over r. Or you could say that the omega A equals omega C equals just 2 omega ABC. That really helps out here for our analysis. So next step, let's take a look at the one of the gears here. And the great thing is that we do one of them, it should be similar to the other one. So we can select, let's select location C. Or I'm sorry, gear C. And we do impulse and momentum here, right? So we're saying momentum state 1 plus the impulse should be equal to momentum state 2. So here we know the I bar, and we're doing gear C. So I bar C, omega C, initially should be equal to 0. And we know that the VC, and we're going to say it's just V bar C initially is equal to 0 because we're at rest. Then we have the external impulses for the gear itself. Now remember, we have two things to consider. There's going to be some force that's going to drive this along the direction of VC, as we had mentioned before, right? So there's going to be some force that gets it to going in this direction. So what we can do is we can isolate these and say this is the center of the gear here, location C. We can isolate these into components, and we say that there's some interaction, because it's a pin connection at C, there's some two-component interaction to the location there. And we can break this into components that, say for instance, we look at one force, right? And I'll call this C. The force is going to be capital C, but instead of XY, this is going to be C, and I'm going to call this tangential, okay, multiplied by the time t. And so I should have another 90-degree opposed direction or force, and I'm going to call this C normal, and then the time there. The reason why I want to do this is because if we were to look at taking our moments about a certain point or so, we can kind of just ignore one of these components, because I'm really only interested in the tangential. I'm not so interested about the normal. And then lastly, I guess maybe I should have put this in a different direction here. In fact, I'm going to do that. I'm just going to put this on this edge here, because I don't know. I think it'll be acting toward the center here. So we say C normal multiplied by the time. I'm also going to have the force having to do with the contact to gear B, right? So since we already used C here, we can call this point D, or maybe just call it the P, a point of contact here. And then there's going to be some force, and we'll just call it a general force that has to do with the contact. And since we know it's going to be rotating in this direction, right, I'm going to draw it to the up to the top left. So we'll say some force multiplied by the time there. So there's no other external moments to this body here. So we just go to the momentum of state 2. We know this is going to be I bar C, and then this is going to be omega C. And it should be moving in that direction. So the inertial term will be the MC multiplied by V bar C. So if we do this correctly, we can just do this once. And so since we're working with the rotating body here, I suggest to start with the moments about, and let's do this a moments about point P. And the reason why we want to do this is because we want to find this force relationship, right? That's kind of acting on our body here. And then we also want to find relationships for the velocity kind of coming with respect to that. And what we could do is we could take this information, and when we look at the rod itself, we can kind of put it in there. So if we do summation of moments about point P, that means I have 0, because I have initial state, and then I add in, then the only force that's causing, then let's do counterclockwise, is positive. It's the only force that's acting to create an impulse that would show up in this, if I'm looking at location P, remember this is location P, is going to be the tangential force there. So I'd say the tangential force CT multiplied by the R, in this case that's just R, remember this, we define this distance as R, CTR multiplied by the T, and that's going to be a negative quantity. This should be equal to, and then I have the I bar C, omega C, and then we can add in the mass, velocity, and the perpendicular distance here, right? So we'd say MC, the velocity, V bar C, and then the perpendicular distance would just be R. Remember, this is location P, and this would be my perpendicular distance, R. And the way that I've drawn this should be a negative here, and this should also be a negative. So I can get rid of the negatives here, right? So I have CT RT is equal to, remember I bar was equal to, for a disk, right, that's equal to 1/2 MC R squared. And the omega C that we had shown up here, omega C, remember, is just 2 times the omega ABC. So that's this term. And then I add in this term. So we have MC. And then we have the VC. Which, if we look, VC is just 2R omega ABC. So 2R omega ABC. And then multiplied by another R. So we can divide out an R through here. This becomes just, this cancels out with this. So we get that CR, it's the CT multiplied by the time T should be equal to 3 MC, and that would be R omega ABC. So like the last problem, we're going to just leave this in place as it stands here. And now we can analyze the rod itself, right? So now if I'm looking at the rod itself, I'd say, and we're going to do our moments again. So that's fine. Looks more like a baguette. that's okay. So this is going to be plus and equals, right? So we're going to do our moments about the center, which is location B, I believe. And we'll go counterclockwise is positive. So before we do that, we need to think about what's going on here. We know in this particular case, since it's a fixed rotation about B, we know the I bar ABC omega ABC initial is equal to 0, right? Because it's at rest. Then I think about all the forces that are acting on this. So we have the applied moment certainly first. That's going to be the MT. Then we have the reaction components at location B, and we can just draw these in. So say BYT, BXT. And now that we're just considering the rod itself, we also have to consider the force of contact between the two discs that are acting here. And so if we're looking at those force of contact, we have to consider both of the forces that are existing here, but they're going to be equal opposite reactions, right? So here, this the tangent's now going to be in this direction, right? So this is going to be like a CTT, right? And we're going to have something similar down here. And this is almost going to be like, and I'm just going to call this equivalent, right? CT times T. Even though it is a reaction for location at the location for A, but I'm just going to call it the same because we know this it does the same setup. We're also going to have that force, but I guess the way we had drawn it inward before, so it'll be opposite now, so it's coming out this way. So it's like a C normal T. And then this would be a C normal T. This should all be equal to, and then finally we get an I bar ABC omega ABC. Now the great thing about doing summation of moments about B is that you don't have to worry about this, or this. We don't have to worry about basically 4 of these impulses in our moments. And the only thing we care about are this, this, and this, which are all knowns, right? And so that's where I'll kind of leave it off. We'll set this up, and that'll be where you kind of end your analysis here. Or you would go continue on, but essentially there, it'll be just working out the problem, the mathematics. So the system momenta for state 1 is equal to 0. And then we add in all the impulses here. And remember, we did counterclockwise is positive. So here we're going to have the CTT, right, multiplied by the radius, though, right? And what's the radius? Well, let's think about this. The radius here from the center, remember we said this is equal to, this length is the L by 2, which is this equal to 2R. So if we want to, we can replace that and say that this is CT2R multiplied by the time t. And then there are 2 of those, right? So we have the 2 forces, right? We have these 2 guys here. They're the same distance away, so we can just multiply it by 2. Plus, and then we have the moment. But the moment, remember, is going in negative direction, so we say minus mt. This should be all equal to. Now the I bar is going in the negative direction, so we say this is negative I bar ABC omega ABC. So this is 4R CT multiplied by T. Remember, we have a relationship for CT multiplied by T up here. That should be equal to, I'm sorry, not equal to, I just have this here. This is minus MT is equal to minus, and then remember the I bar here is the 1/12, and that would be the M ABC multiplied by now the total length square, or I'm sorry, yeah, the total length squared, so this would be L squared, or, yeah, squared. And then that's multiplied by omega ABC. And then we can put in for what we know here, right, that QT is. So, or I'm sorry, for what CT is. CTT. That's just equal to the 3MC R omega ABC. So this would be 4R multiplied by 3MC R omega ABC. And that's multiplied by time t minus mt is equal to negative 1/12 MABC L squared omega ABC. And I think most of these terms are known here, but if I wanted to find this, I could just move some things around. Let's just make this MT is equal to 1/12 MABC L squared omega ABC. And that's minus 12 MC R squared omega ABC T. And then I would just divide through by T to get my moment, right? And so I will leave that to you. The rest of this should just be an algebraic manipulation of the problem, and it should be kind of straightforward from there.